All right, this video is for calculus, and we're talking about the unit that covers parametric equations, polar coordinates, and vectors, transitioning now to the vectors part. The reason this is included in this unit is because vectors has a kind of computational connection to polar coordinates, but it is kind of its own thing. All right, so what is a vector? A vector is a directed line segment, or you can think of it as a distance in a known direction. It's characterized by the length of the line segment and the direction. We have a notation convention for distinguishing a vector from a point. If we're talking about a point, then we use curved brackets like this, and that indicates that we go a certain distance x and y in a rectangular coordinate system to get there. If instead we want to talk about a vector is a distance in a direction. So it's a translation. It's like a translation, right? So it has a starting point, an ending point, and it moves in a direction, right? So in a sense, this is that you're moving a certain amount in the x and you're moving a certain amount in the y, but it's not like the destination, which is a point. It's the distance itself. That's the vector, okay? The movement, if you want, or the translation. So to distinguish that, instead of using curved brackets, we use angle brackets when we're talking about a vector. And then typically we will name a vector with a letter. So if you decide to use, like, say, v, you have to indicate that that is not just a regular variable or something, a point. It's a vector, so we use a little arrow over it like that. Now in the textbook, they will just make that letter bold, but when we write things, it's very difficult to indicate something's bold. So I will be using a little arrow over the top to indicate that's the name of a vector. All right, so a vector can start at any point, but if you place its what we call the initial point, that's where the vector starts. The terminal point is where it ends. If you place it at the origin, then the distance here works just as if you were locating the points from 0, 0. The ending point is at 3, 4. So since it's a translation, that means to go in this direction, you have to go a distance 3 in the positive x direction, and you have to go a distance 4 in the positive y direction. So you put a positive 3 in the x spot here, a positive 4 in the y spot there, right? You can also figure out the amount of translation by, if you're given the points, you can figure out the translation by saying you're going to take the ending x minus the starting x, and that will give you the translation. So that means we want 3 minus 0 in the x direction to get a distance of 3. And then to get the second coordinate, if you have points, you can take 4 minus 0, right? The ending y minus the starting y. So 4 minus 0 gives you a translation of 4. If I want to know the length of the vector, the name for that is either length or more commonly we call it the magnitude of the vector. Magnitude is a word that means the length of the vector. The symbol for it is whatever symbol we've used for the vector, we put a line around it like this, a pair of lines. So it kind of means the same as absolute value. Some textbooks put 2 lines. I'll stick with the 1 line convention, but if you want to use 2 lines or your teacher prefers 2 lines, that's fine, right? You can use 2 lines or 1 line, means the length of the vector. And that means that since we have an x translation and a y translation, that length, that magnitude is simply, since x squared plus y squared equals the length squared, the length is just the square root of the sum of the squares of the 2 legs, right? So it's just the square root of what we call the x component squared plus the y component squared. And the tangent of this angle from the x-axis is the y-coordinate over the x-coordinate. So hopefully you can see the connection to polar here. This is basically the same idea as polar. Remember we said for polar, x is r cosine theta, and y is r sine theta, and the radius is the square root of x squared plus y squared. And the tangent of the angle is y over x. That's for polar. So this is exactly the same, right? You can define a direction angle called theta, and that is counterclockwise in radians from the x-axis, the same as with polar. And that means that if you want to take a vector's x and y components and turn them into a magnitude and a direction, the magnitude equation is the same as the equation for r. So you can think of it as kind of like r in polar is the length of the vector. And the direction is tangent of the direction is the y component over the x component. And if you want to go the other direction, this is important too, these equations will take a length and translate it into its x and y components. So if you take the length, the magnitude of the vector times the cosine of its angle from the x-axis, that will give you the x component of the vector and the y component. That's what we're talking about on the next screen. So if you have the magnitude of the vector, let's say we know that the length of this vector is some magnitude and we know its angle, and the angle is always defined the same way it is for polar, counterclockwise in radians, unless the problem asks for degrees, and it's counterclockwise from the positive x-axis towards the y. Then if you imagine that you shined a flashlight perpendicular to the x-axis here, the shadow this would cast is called the x component, or the component in the x direction of the vector. And if you shined a flashlight this way, it would cast a shadow of length y. And those things are simply the same as converting from polar. So let's say that I have a vector that is 5 long, right? If I had some angle here, and this, let's say, was, well, I'm going to use degrees here, because actually a lot of times we do things in degrees when we're talking about vectors. If I want to figure out the x and y components, this x component is simply 5 times the cosine of that angle. And this y component here is 5 times the sine of that angle. Right? Same as we would for converting for polar. This is like the r cosine theta. And this is the r sine theta, except that in this case, the r is the magnitude of the vector. The magnitude of the vector here. Okay, if this is the magnitude of, say, vector b. Okay? Those are also referred to as projections, projection of the vector onto the y-axis or onto the x-axis. All right, so rather than memorize new formulas, just use the polar formulas that you've already memorized. They're the same. All right, so a couple of other key things. A vector is defined by giving its initial and terminal points. You can find the components by subtracting, like I said. If you wanted to define vector w as the vector from the point 1, 2 to 2, 2, 4, 6, then you can find its x component by taking the ending x minus the starting x, 4 minus 1, to get that we moved 3 in this direction. And then in the y direction, you can take the ending y minus the starting y. So 6 minus 2 is a total of positive 4 translation in the y direction. You always have to do end minus start, though, so that you get the right direction, so it goes in the right direction. If you reverse these, then the arrow's in the other direction. And vectors are indicated geometrically with an arrow. Right? So two vectors are considered equal if they are the same distance in the same direction, regardless of where the vector is located in the xy plane. So if you have a vector that starts at 0, 0 and goes to 3, 4, so it goes 3 over and 4 up. And you have a vector that starts at 1, 2 and ends at 4, 6, and it goes 3 over and 4 up. These two vectors are considered equal. Right? So the vectors can be kind of freely moved around because they're just about translation. They're not about location. What happens if you add two vectors? So if you add two vectors, let's say we have the vector 3, 4, we can call that vector A. We have the vector 5, 1, we can call that vector B. What happens if I add them? Well, that means that you've translated a total of 3 plus 5, or 8, to get to this point, and you've translated a total of 4 plus 1 more, which is 5, which suggests that we can simply add the components. And this is what we do. So if we have vector A is 3 plus 4 and vector B is 5 plus 1, then what we're going to do to find the x component of the sum is we're going to add the two x components together to get 8. And to find the the y component of the sum, we're going to add the y components together. Okay, so geometrically what's going on is if you start with one vector and you draw it in its location, remember we said that it doesn't matter where the other vector is. So although 5, 1 could be drawn, with the start of the origin, we're free to move this second vector around. So you can position it so that it starts with its initial point at the terminal point of the other vector, so that you go one vector and then you move another vector, and then that will produce an overall resultant vector, which is the sum of the two. This is sometimes called the triangle law. So if you take one and you put these tip to tail, then the long starting at the initial point and ending at the overall ending point, that vector is the vector that results from the sum. So geometrically, you can figure out what's going on when you add, and algebraically, this is how you would compute the components of the sum. Vector addition is commutative. It doesn't matter if you start with A and put B onto the end of that, or if you start with B and put A onto the end of that, you're going to get to the same spot. So A plus B is the same as B plus A. And sometimes this is called the parallelogram law, because you could also think of it as take the A vector, take the B vector, and have them start from the same initial point. And then if you form a parallelogram, the diagonal that bisects that parallelogram, that is the sum of the two geometrically. Right? And of course, it doesn't matter what order I add these in, I'm going to get the same number 8. Right? So commutative law applies to vector addition. What about multiplying a vector? Well, in this course, we're going to talk about how to multiply a vector by a number that isn't a vector. So to distinguish that, we call that number a scalar. And what happens is, if you multiply by a scalar, like let's say we have 3 times A, if A is say the vector 1, 2, actually I don't think this is to scale, and we take the vector 3 times that, it's 3 times that vector, you can just imagine distributing that in there. That means that each of the components is individually tripled to 3, 6. And that means if this was going in this direction, 1, 2, this is the same direction, it's just 3 times as long. That's why this is referred to as a scalar, because it scales the length of the vector. It doesn't change the direction, but it scales the length of the vector. And of course, you could multiply by fractions. If you multiply by a negative scalar, then you're scaling by a certain amount, but you're also making it move in the opposite direction. So some people will call this a different direction. I like to think of it as the same direction. We're just going along the negative part of that line instead of the positive part of the line. So if you multiply by a negative 3, the vector 1, 2 becomes negative 3, negative 6, so it goes in the negative x direction, the negative y direction. So I consider that to not change the direction, it's just moving in the negative part of that number line. So how do we subtract a vector from another? Well, if we want to take the vector A minus B, and let's say the vector A is 3, 4, and the vector B is 5, 1, then first we can say that's the same as adding the negative of B. So I can take the vector A, which is 3, 4, but first I can take the vector B and multiply it by a negative 1. So I get negative 5 and negative 1, and then I can just add the components up here and add the components up here for the y. Right? So, what I would actually write is this. I would say if you're telling me to take 3, 4 and subtract 5, 1, I'm just going to apply this operation to each thing individually. 3 minus 5 is negative 2, and 4 minus 1 is 3. Simple as that. Okay. But what's happening geometrically is we are maybe starting with vector A, right? And then we're taking B, which if I were adding would be here. First, I multiply it by negative 1, which flips it and makes it go this direction. So then when I add that negative B onto A, I get this vector. So this is the vector A minus B over here. Right? So you can do it that way. That's the way I prefer to think of it. But you can also do this. If you take a vector A and a vector B and you have them starting from the same location, you can make the parallelogram like we did before. This bisecting diagonal here, that's the sum of A plus B. The A minus B vector is the other diagonal, and it goes from the ending vector to the starting vector. So if this is A minus B, it starts at B and ends on A. Kind of interesting. We use that fact a little bit in Calc 3. All right, so there's some properties of vectors. Now here, when we don't have arrows because they're making these bold. So these are vector. Vector A plus B is equal to B plus A. You can have a 0 vector. It means all the components are 0, so 0, 0. If you add 0 to A, you get itself. If you have a vector and you multiply by a scalar of 1, you get itself. If you take a vector A and add the negative of itself, you get the 0 vector. If you take a scalar and you decide to first add vectors and then scale everything up, you can individually distribute this and scale each one separately and then add. And if you have multiple scalars multiplied and then multiplying, scaling up a vector, you can scale up by one first and then scale up by the other. If you have 3 vectors, then you can combine them for addition in any order. A plus B plus C is the same as A plus B first plus C. It doesn't matter what order you do them in because it's all commutative, right? And then if you have scalars like C plus D that are both multiplied by a vector, you can distribute the vector. It's C times A plus D times A. So in many respects, the vectors work the same as numbers. All right, we're going to do a few examples here and then finish with 2 kind of applications that are a little bit longer. The last example will be the longest. First, show these 2 vectors are equivalent. This means a vector from this point over to that point and from this point to that. So the u vector here, what I would do is do the end minus start. So the x component is the end x minus the starting x, and the y component is the end y minus the starting y, which means this is 5, 8. We translate a total of 5 in the x and 8 in the y. The v vector here, if I do that start minus end, is 7 minus 2, and then 7 minus negative 1, which is 5, 8. And so we've shown that those 2 vectors are equal. They're equivalent. All right. Find the magnitude of each vector and the vector 3v minus 2u, and then sketch the original vector and those vectors. Okay, so let's find the magnitude of the vector. The magnitude of this first of each vector. What's the magnitude of the u vector? Here's the symbol for it. It's the square root of the sum squared of the components. So that would just be 9 plus 36, which is, I won't have to drag a calculator out for this. Turns out to be square root of 45. And in decimal, that's about 6.7, roughly. 708, I guess I'll use the rounding rules. The magnitude of the v vector is the square root of its x component, 5 squared, plus its y component. Now, technically, this is negative 2 squared, but you don't even have to bother with the negative because we're going to square it. This is the square root of 29, which turns out to be 5.385. Okay. And then we're being asked to compute a new vector, which is 3v minus 2u. Okay, so what I do for this is I write in the vectors. So the v vector is the vector 5, negative 2, then minus 2, and the u vector is 3, 6. Okay, multiplications happen before addition and subtraction, just like with numbers. So I'm going to multiply this 3 in and get 15 and negative 6. And then I'm going to multiply this 2. I'm just going to multiply the 2 in, so I'll keep that a minus. That's 2 times 3 is 6. 2 times 6 is 12. Now I'll do the subtraction. So 15 minus 6 is 9. Negative 6 minus another 12 is negative 18. So the result of that is the vector 9, comma, negative 18. All right. Then it's asking me to sketch all these vectors. So let's do that. I'll make a big sketch here. I have some big numbers here, so I'm going to actually make the sketch like this. This is x and y. And let's see, I'm going to go up to negative 20 by 2's. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's negative 20. 2, 4, 6, 8, 10 over here as well. All right. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. So that's 20. All right, so a decent scale there. Let's go ahead and put these vectors on. So the vector u, that is 3, 6. So if I just put u on there, it means I'm going to go over, let's see, 2, 3, so that's 3 and up 6. 2, 4, 6. So something like this. This is the vector u right here. Okay, that's a u. The vector v, if I do that on the starting at the origin, although we could start anywhere, is 5. So 2, 4, 5, negative 2 would be here. So this is vector v. Okay. And then what about this? This is 3v minus 2u. So let's try graphing that. So first, what's 3 times v? 3 times v is in the same direction here, but it's 3 times longer. 1, 2, 3. So this is roughly 3v is 3v that. Okay, something like that. And then I'm subtracting 2u. So if u is in this direction, that would be this direction. There's u. Negative of that would be this, and 2 of those would be this. So this is like minus 2u. So if I added a negative 2u onto a 3v, we should get this vector here. Sorry, that's kind of wobbly, which is, yeah, over about 9 and down about 18. Right, so not perfect sketch here, but that's the idea. Okay. So I think you see, once you see how it works, it's pretty straightforward. Okay, to finish this lesson, I'm going to do 2 applications of vectors. Now, this is not stressed in our class, but it's kind of more of a setup for stuff that's going to come later. Things to know. Sometimes you're dealing with, you have to define what the vectors represent. If objects are moving, then a lot of times we're having the vectors represent velocities, right, or motions. If objects are not moving, then often, since nothing's moving, the vectors are representing forces. And in that case, if the object's not moving, the sum of the forces has to be 0. So I'm going to show you 2 quick examples. The first one is a moving example. So let's say a boat heads across a river at a speed of 4 miles per hour. But the water in the river is flowing downstream at a rate of 2 miles per hour. What is the resultant, that should be speed and direction of the boat? Okay, so if there's a boat that's starting here and heading straight across, I'm going to represent this with vectors. I'm going to say, all right, the boat is going to have a vector. Let's call that vector b. The water is going to have a vector. We'll call that vector w for water. And then the resultant vector we'll call r. So that means that since r is the result of the sum of the boat's motion and the water's motion, we can say that the resultant vector has to be the boat vector plus the water vector. So then I'm going to figure out the vectors for each of these. Now, I'm going to show you 2 ways to do this, okay? For the boat, we could just by inspection, well, first we're going to have to put a coordinate system on here. Let's do that. Let's define this to be x and this to be y, and the origin is the initial location of the boat. So that's 0, 0. Okay. So this boat, hopefully you'll agree, it is moving in the positive y direction, which means its entire 4 miles per hour. Vectors are going to represent velocities here. So that means the boat vector is 4 miles per hour in the positive y direction. Okay. Now there's another way I could get that. If I want to kind of have a standard way to do that, I could use the length and the angle. So what is the angle for the boat's vector? The angle for the boat's vector is, and I'm going to use degrees here. Often in vector problems, we switch to degrees instead of radians. So if I wanted to figure out its components, right, I could also have done this. I could take the magnitude of the b vector times the cosine of its angle. That's the x component, like r cosine theta in polar. And the magnitude of the b vector times the sine of the angle would give me the y component, like r sine theta. So this would be the magnitude of 4 times the cosine of 90 degrees. And this would be 4 times the sine of 90 degrees. And the cosine of 90 degrees is 0, so this is 0, and the sine of 90 degrees is 1, so I get that 0, 4. Now, it wasn't really necessary for me to do that because this vector happened to be pointing straight up. But if it was at an arbitrary angle, then I would need to use this to take its length and break it down into components. Let's do the same thing for the water vector. I can see by inspection that this 2 miles per hour is completely in the x direction, right? But I could also have defined that the angle for that vector, since it's pointing in this direction, is 0 degrees, and said that the water vector is the magnitude of the water vector times the cosine of its angle for the x, the magnitude of the water vector times the sine of the angle for its y, and said, oh, that's 2 times the cosine of 0 degrees, 2 times the sine of 0 degrees, to get that this is 2 times 1, 2 times 0. Okay? But whether or not you use the direction and angle, the magnitude of the angle, or if you just by inspection get these, that means that the boat vector turns out to be 2, 0, and the water vector turns out to be 0, 4. So that means the resultant vector here is the sum of those two. It is 2 for the x and 0 plus 4. So this is the resultant vector. Now, what is the speed? The speed, since this is a velocity, is just going to be the magnitude of that resultant vector. So that would be the square root of 2 squared plus 4 squared, which turns out actually to be 4.472, and the units there would be miles per hour. Right? So if you're going 4 miles per hour this way, and you're getting pushed 2 miles per hour this way, your speed relative to the Earth is actually 4.47 miles per hour. And if I wanted to know this angle, I could say that the tangent of that angle, let me use a different color here, the tangent of that angle has to be the y coordinate over the x component, which is 4 over 2. And I could then take the inverse tangent of 2, which turns out to be in degrees 63.434 degrees. So I could also tell the direction that I'm going. So this kind of stuff is really useful for, say, navigating in planes where you have wind pushing you around and you also have the engines pushing in a direction. Right? So you could have motion, and in this case, the vectors represented the velocities. Okay, the last example to finish up this video is going to be something where something's not in motion. So we're going to use vectors to represent forces. All right, so let's say a star-shaped decoration is suspended motionless from 2 points as shown in the figure. If the decoration weighs 10 pounds, which is already a force in the imperial system, find the tension in each wire, the magnitude of each tension, as well as the component forces. All right, so we're going to impose a coordinate system here. It's going to be where the connection is there. This is x and y. And then I'm going to have 3 different vectors that are all acting on this object, right? One is the weight of the object. So I'm going to call that W for weight. And then this, we're going to call this tension 1, which is the force inside this wire. And this is going to be called tension 2, right? And since all of these forces are perfectly balanced, because if they weren't, this would be moving, that means that if I add these up, if I take tension 1 vector plus tension 2 vector plus the weight vector, it has to give me the 0 vector, because otherwise there would be motion. Okay, the forces are all in balance. All right, so now I have to come up with each of these vectors. Let's start with tension 2 for a second. So tension 2 has this angle right here as its angle. Would you agree? Because angle is from the x-axis counterclockwise towards the y. And because of the geometry here, this is an alternate interior angle with 40 degrees. So that means its angle is 40. So for tension 2, I'm going to write that first. Tension 2 is some currently unknown magnitude of tension 2 times the cosine of its angle, which is 40 degrees, and some currently unknown magnitude times sine of 40 degrees for its y component. So that can be broken down into an x component and a y component. This is whatever the tension is times cosine 40, and this is whatever that tension is times sine of 40. Okay, then let's do that for tension 1. Okay, tension 1 has its own angle, but from the x-axis, it's this angle, right? And since this angle here is 52, this angle is 180 minus 52, which is 128. Right? These have to add up to 180 degrees. That's 52. This is 52. There's 128 left. So I'm going to break tension 1 into its x and y components, just using this standard form. I don't know what that magnitude is, so I'll put it in as a variable, times the cosine of its 128 degree angle, magnitude of T1 times sine of 128. Okay, that breaks the T1 tension 1 and tension 2 into its x and y components. Okay, for the W, I'm just going to by inspection say that its weight is 10 pounds and it's completely in the negative y direction. So I don't need to use this cosine thing. It's just 0 minus 10 pounds, negative because it's in the negative y direction. And now I'm going to make a vector equation here. I'm going to say T1, which is magnitude, actually let's use the right coloring here. T1 was this, T1 times cosine of 128, T1 times sine of 128, that's T1, that's this, okay, plus T2, which is an unknown magnitude 2 times cosine of its angle 40 degrees for its x component. The y component is the unknown magnitude times sine of 40, okay, plus the weight vector, which is 0, negative 10, that has to equal the 0 vector, which is 0, 0. Okay, so this is called a vector equation. And we have some unknowns here. There's actually two unknowns. There's the magnitude of tension 1 and the magnitude of tension 2. But luckily, because we have x and y components, we can split this into a system. So what I'm going to do first is take all the x components, because they have to be equal. These are at right angles to each other. They don't affect each other. So taking the x components, that would be, I'm going to write this slightly differently. Cosine of 128, that number times the magnitude of T1, that's this, plus the x component here, but I'm going to write the number first. Cosine of 40 degrees times magnitude of T2. Okay, I'm omitting the errors just because it's getting too messy. Plus the x component here, which is 0, has to equal the x component on the other side of 0. So there's an equation for all the x components. And the y components have to all sum on the left to be 0 on the right. So this would be sine of 128 times magnitude of T1 plus sine of 40 degrees times magnitude of T2 plus negative 10 has to equal 0. And now I've got a system of two equations with two unknowns. So what I'm going to do to solve this system is use a calculator and use RREF. Okay, but first I'm going to move this to the other side. So I'm going to instead make this, I'll write it one more time. So it is going to be cosine 128 degrees magnitude T1 plus cosine 40 degrees magnitude T2 equals 0. And then this is sine of 128 degrees T1 plus sine of 40 degrees times T2 equals, if I move this to the other side, it's 10. This is the system I'm going to enter. Okay, so we'll grab a calculator and put that on the screen. I'll use the matrix for this. Let me make sure I'm back in functional mode. Yeah, let's go back to that. Functional mode. Don't think that matters, but just to be safe. Okay, second matrix, go over here and edit a matrix and make it 2 rows and 3 columns, so 2 by 3. And then I'm going to enter, oh, I got to be in degree mode, sorry, because I put degrees. So let's be in degree mode here. Okay, back in there again. Matrix, edit. Okay, 2 by 3. So I'm going to put cosine of 128, and as soon as I hit enter, it's going to convert that to a decimal. And then this is cosine of 40 equals 0. And the second row is sine of 128. You could use other methods to solve this system, but I like the calculator method. Sine of 40 degrees, and then 10. Okay, now that that's in there, I will do RREF. So back to the matrix menu over here, scroll down to RREF, reduce row echelon form. We'll operate on matrix A. And that gives me this. So after I do my RREF, I get this matrix. 1001, and then there is numbers here. So they are 7.6551, 7.6, I'm going to write actually the whole number down, 665193811 to illustrate something. And then the other number is 6.16036748, which means that since this first column was T1, then the magnitude of T1 is this. So we just found out that the force in the wire T1 is 7.665193861 pounds. And the force in the other wire, T2, is only 6.160367483 pounds. Okay, so that if we're doing an engineering study, we'd want to make sure that the wire that we choose can handle much more than this weight so it doesn't snap, right? And then if we plug those back into these, let's actually write the vector form of these tensions. So tension 1, I'll put that in red. Tension 1 as a vector is that number 7.665, I'm going to abbreviate a little bit, times cosine of 128, that its x component, that magnitude 7.665 times sine of 128. And if you use the unrounded numbers, this comes out to be, I'm going to now round it, this comes out to be negative 4.719 for the x component and 6.040 for the y component, and that's in pounds. Right? The other wire, tension 2, as a vector, is its magnitude 6.160 times cosine of its angle of 40 degrees, magnitude 1.60 times sine of 40 degrees. So its x component ends up being positive 4.719 and 3.960 pounds. Okay, so what's happening here is the tension, okay, the tension in 1, so this number here is negative 4.719, whereas the other tension has positive 4.717. Sorry, they're balanced. These exactly balance out and cancel. Sorry, this is actually a 9 in both of these. 9. So they exactly balance so that the object's not moving. And in the up and down direction, the y components sum up to be exactly the 10 pounds needed to balance the weight. Right? And the reason that this wasn't exactly perfectly balanced was because of the asymmetry in these angles. Right? If you were to move this star to be directly underneath this, then tension 2 would have all of the weight and none of the weight would be in the other wire. Because it's unevenly balanced, there's actually more weight being in one of these wires compared to the other. All right, so this allows you to analyze structures like that. Okay, we're not going to do questions like that on our test, but I thought it was important for you to see, why do we bother to study vectors, besides the other things that we're going to study, which are speeds and accelerations.